this is where we finished in the first hour. Okay, so I'm going to be switching the screen because, as you know, the recording is only done in one of them. So, but this is the last equation that we end up with. This is what is called the weak formulation, okay, the famous weak formulation, and it's always the first step when you solve a problem using finite elements, always. Okay? The process is you get a partial differential equation, and the first thing you need to do is write your weak formulation. Right? Next, because still the objective is to find the displacement. Okay? We are after this u here. It's a displacement field. And the reason why I decided to put some things on the left, some things on the right, is precisely because on the left is your unknown, which is the displacement. Okay? On the right is everything known. F is the external force, is data. Okay? It's something that you know. And then the boundary conditions, so known stress in one of the ends, is also data. Okay? And we still need to know how to impose displacements, because I was very happy to get rid of the displacement, if you remember. Okay? I only used stresses known at the right. I haven't used the known displacement at the left yet. But everything is data here on the right. How do we find u is the question. Right. And in order to find the displacement, we are going to first start by meshing the domain. So you have your bar that goes from 0 to L, and we are going to subdivide this bar in elements. Okay? Here I'm using 3 elements, okay? 3 little intervals. They don't need to be of the same size, but here I'm using them of the same size. The elements are here in red, and then I have nodes, which are in blue, and we have 4 nodes, 3 elements in one dimension. Important here, there are 2 types of numberings. Okay, and this is probably one of the most important things at this point. When you look at the nodes in the whole bar, you have what is called the global numbering. Okay? The node number 1, the node number 2, the node number 3, the node number 4, etc. Okay? But when you look and you focus your attention in only one element, this element only has 2 nodes, the first and the second. And this is the local numbering. And this is going to be crucial, especially when you think on putting this into a computer. Okay? This is how we are going to be able to program things properly in a computer language. So the way you store a mesh in a computer is with a matrix. You store what is called a connectivity table or a connectivity matrix that says in the first row the nodes that correspond to element number 1. So element number 1 has nodes 1 and 2. You can see it here. Element number 2 has nodes 2 and 3. And then it's what you see here in the second row of this matrix. Element number 3 has nodes 3 and 4. Right? And the column of this matrix, what is telling you is the local numbering of the element. For example, for element number 2, the first local node is the node number 2 with global numbering. It's simpler than it looks. Okay? But this is just a way to store a matrix, and that's it. This is how the computer sees a mesh. A simple matrix of numbers. Okay? So that's the first thing that we need. Now, why a mesh if what we are after is a displacement field, okay, a function u? Because we are going to use this mesh to build a particular and very simple approximation of the displacement. We got the mesh. The next thing we do is we associate to each node a shape function. So we got a mesh from 0 to L, from 0 to 0, no, from 0 to L, right? And we have introduced some nodes here. Okay? And then what we're going to do is, for each node, for example, this is node number 1, 2, 3. For node number 4, the shape function associated to it has this hat shape. Okay? It's 0 everywhere except in the 2 elements touching my node, number 4. And this is the shape function N4. Okay? We can associate to each node one of these shape functions. Why not? Right? And the key, and this property, I'm going to be talking about this property from today, first lecture, to the last. The key is that the shape function N4 takes value 1 at the associated node, 0 at the rest of the nodes. That's the only property you need. Okay? N4 here is 1 if I am looking at it from node number 4, is 0 at all the other nodes. So at x1, x2, x5, and so on. All the other ones that are not x4. And it's linear, piecewise linear. Okay? So if I'm telling you the value that has to take at this point and at this point is 0 in both nodes, and it's linear, the only possibility is that it's 0 in between. Okay? And it's 0 at number 2 and it's 0 at number 3, linear, has to be 0. And it's 0 at number 3 and 1 at number 4, linear, has to be this straight line in here. That's the only thing we know about the shape function, nothing else. We don't need anything else. Right? And once you've done that, we are going to find the approximation of the displacement. We are going to call it U bar. Okay? The difference in between U and U bar is that U is the exact solution. We don't know it. U bar is the approximate solution, and we are going to be happy with approximate solutions here. Right? What type of approximate solution we are looking for is summation of coefficients and shape functions. Okay, let's put the x in here. And I'm using the same notation as in the nodes. N plus 1 nodes, this means n elements. These are coefficients, numbers, I mean. Okay? They do not depend on x. And these guys here are what we called the shape functions, which is what I just described in the picture above. Make sense? Yeah. Right. If my objective was to find U, right, and I have defined this mesh, given the mesh, the shape functions are naturally described. Okay? If I put some points, automatically I know the shape functions. Do you agree? Because they are just given by the points. So, if my objective was to find U, what is my objective now? After I decided this kind of approximation for U, what do I need to find? This is 50-50, right? So you got two things in this formula. You can flip a coin and try it. I don't know. What is the objective now? Shape functions. It was 50-50. Shape functions, I know them. As soon as I put the points, they are known. Now it's not 50-50. Now it's 100. Okay? Go for it. The coefficients. These are my unknowns now. The coefficients. Is it clear? If I put the points, the shape functions are known. They are like this. Okay? The only thing I need to do is decide how many points and where these points are. But this is a choice. I can make it. Everybody agrees? Yeah? So, this is looking good because the objective was to find a displacement function. It's very difficult to find a function, right? But now, what we need to find is a bunch of numbers, a bunch of coefficients, as many as points in your mesh. Okay? So the more points you put in a mesh, the more coefficients you need to find. As a result, it's not, you don't need to be very clever for this. The more points you put, the more accurate will be the solution. But the more coefficients you need to find. So there is a trade-off here. Right? Right. What we are going to do for the rest of the hour is how do we find these coefficients for this particular problem. And then we will extend it to other more complicated problems. Right. Go back to the slide. So what do we have here? We have this choice. I want to emphasize that this is one possibility. Okay? I think it's the simplest one. Because what we are doing here is we are saying that the displacement, which is something that could be very, very complex, we are going to approximate it with something that changes linearly in between one point and another. Change linearly. I cannot think of anything simpler than that. Okay? And that's why this particular choice. And this linear variation from one point to another, this is how we write it, in terms of these hat functions, which are easy to build effectively. Right? Now, if this is the expression of the displacement I'm looking for now, the derivative, come on, trivial, because in order to differentiate the u hat, these are numbers, q's are coefficients, I differentiate these shape functions there. Right? And then what about this phi? I've been ignoring this phi for a while. Right? I introduced it here. Okay? I put it there. And I put in here a sort of, I don't know, this looks like a bit of magic for all test functions phi. And everybody says, yeah, good. But what does it mean and why do we put it? Okay, this test function in there. I'm going back to explain that. I'm going back here. And I'm going back to this picture here. And I am going back, but you cannot see anything. Now you can see something, right? I'm going back to this picture, right? And I said, careful, because if you don't introduce this phi, if you just say the integral of the residual equals to 0, so if you don't introduce this phi, if you just say the integral of this residual equals to 0, you are accepting this kind of residual, this one here. Which is really bad, because I said on the left, on the red dot, is really bad. I don't have equilibrium of forces at all. My residual is not 0. Right? So what I said is we introduce this test function. How is this helping this test function? Well, you can think of test functions. Think on something like this. Is a function that does a little mountain in here and is 0 everywhere. I should have used another color. So it's a little mountain here and then 0 everywhere. Okay? If I have this type of test function, when I multiply this little mountain with my residual, what am I doing? What do I do when I multiply this little mountain with my residual? this mountain here, I multiply it with a residual in orange. What am I doing effectively? Well, I'm saying, help you a bit, I'm saying whatever happens here, I don't care. Because when I multiply something by 0, it's 0, correct? So using this kind of mountain here is the same as saying I'm going to make sure that the equilibrium is well satisfied in the green area. It's like making a zoom. You remove all the part that you're not interested because you selected this mountain that is 0 almost everywhere, and just focus on an area. Can you see that? You understand that? Yes? Okay. So that means that you will not accept this solution as a good solution. Because in this area, in green, the residual is really bad here. Make sense? Or not? I can see some faces that worried. Right. Let's show it. I mean, if you have this residual, do you agree with me that the residual, if you integrate it on average, is 0? Okay? But if I plot the product of the residual with this little mountain, what is going to happen is that you're going to have something like this. And then we need to be a bit good on plotting, which I am not the best. At each point, at this point in here, I need to multiply the residual by the mountain. That's a 0. Okay? At this point in here, the residual is quite high, multiplied by a little number here, so it could be something like that. Yeah? The product of two numbers at every point. So here, the residual has grown, the other thing has decreased, I might be here. And then you advance, and at some point, no matter what the residual is, the mountain has gone to 0, correct? So from this point on, I will have something like this, and then all 0. That would be r dot x multiplied by this phi. That's why I'm trying to illustrate here. Better or not? I'll keep trying, if not. Okay? So, all of a sudden, with this residual in blue, you were happy if you just ask for residual to be 0 on average, but if you are asking for residual weighted with this phi to be 0, then you are not going to be very, very happy with this residual because you have a lot of area here. This is far from being 0, which is what you are asking with an integral. You are asking for an area to be 0, right? So by weighting, by using these test functions, this is what you're doing. You are asking for the residual to be 0 in all the domain, window by window, area by area, right? Because I can use this little mountain in here, phi 1, or I can use phi 2 now. And then I will use phi 3. And by asking for all these weighted residuals to be 0, I'm going to make sure that not just in average in the whole domain, but in small portions, I also have equilibrium. Rather than asking for average in a huge domain, I will ask for average here in a small portion, and then on average in another portion, and then on average in another portion, and so on. And as a result, I will have a better approximation of my displacement field. Does now make a bit more sense? Sorry?
No question.
No? Nothing? Nobody? It's just an interpretation because I know that 80% of this class has gone through the level 3 finite elements doing that. And the first thing I did when I started teaching this module is I asked the question of why and not a single person knew. So I'm just revisiting that part, okay? Not just the procedure. I'm not just interested in procedure, sorry. I'm interested in that you understanding the process so that you don't need to memorize anything. You just know where things are coming from. Okay, so what mountains are we going to select for these test functions? Surprise, the same hats, the same ones, okay? My phi is coefficients and the same shape functions n that I used here, exactly the same ones. Right? They have a similar shape to what I plotted, so they are going to have this effect of focusing and making sure that the approximation is good in one area, and then moving on. Yeah? Okay. So what is next? Bit of manipulation as usual. What we are going to do now is remember the weak form. This is the one. A, E. Sometimes I'm not writing the whole dependence on X, okay? When I write here, I'm writing A multiplied by E, okay? But in general, in the lecture notes, I am more precise. I'm saying the area of the cross-section could change. You don't need to have constant area of the cross-section, okay? This is my weak form, so I'm just copying what you have at the bottom of the slide. And then the boundary term. Right, 3 area and this test function, okay? Just copying this expression. And then this is where we are. So what I'm going to do is here, I'm going to introduce, or if you like, here, I'm going to introduce the approximation, okay? This one, which is a summation of coefficients, we call them Q, and derivatives of the shape functions. Similar stuff here. We have the phi bar, this one, okay? Same stuff with different coefficients, okay? So it's the same shape functions but with different coefficients. And for the moment, I'm going to focus on the guy on the left, okay? So this guy here for the moment. Then we can look at the right-hand side, but let's go step by step. Yeah, ready? Now it's a lot of formulas. It seems very, very complex, but it's not. So we insert these expressions, and we have integral of A, E, and a summation. And then another summation. But we know that the integral of a sum is the sum of integrals. So actually the summations, we can put them outside. So that would be summation of, let's see if I can do this, just to make sure that we can follow exactly where each summation is going. There you go. So I'm going to put the one in green first. Doesn't matter, because you sum one or the other first, it doesn't matter really. Okay, and then I have another summation. And then the integrals. And I'm going to write it like this. I'll put this here. I'm going to put the integral. And I got the area, the Young modulus. Okay. What of the terms that you see in all these big expressions here? What are the terms in this integrand here? Here. That do not depend on x. Just checking that I haven't lost you on the way. What things are not depending on x? Someone said something. The coefficients. The coefficients are not depending on x. And I have coefficients here, and I have coefficients here. If something is not depending on x, I can take it outside of the integral, right? That's why I'm asking. So the only thing that I need to keep inside are these derivatives of the shape functions, because the shape functions depend on the position. Okay, they are these hats. And I'm going to write it like this. And then I'm going to put this coefficient here and this coefficient here. You can put them, both of them on the right if you like, but I prefer to put the green with the green. So I'm going to do it this way. Yeah? No questions? Nothing? Right. And on the right, what do we have? We have this guy here, okay, which is the integral of f multiplied by this phi. That means summation okay, and that's it. So actually the right hand side, as you can imagine, is always simpler. Is simply summation, and inside the integral I only need, oops, no one complained here, but my shape functions are not differentiated here. Okay, on the right hand side I don't have derivatives. On the right hand side, f multiplied by this phi. No derivatives. That's the difference with respect to the left hand side. Okay? So the shape functions are not differentiated. And inside the integral is the external force and my shape function. That's it. Do I still have you with me? Yeah? Okay, so, and then obviously, but this one is too simple now. Okay, the one here on the right is the simplest one because there is no integral, there is nothing there. Okay. But you still can write it if you need to. This is, go back, you always use the same stuff. This is phi, okay? So you need to evaluate phi at L, so that is the summation of coefficients multiplied by the shape functions at L. Yeah? Happy? Okay. Now, what happens here, and I'm going to make use of the slides a bit now. What I've done is basically these two lines. This is what I wrote on the tablet myself. It's exactly what you have here written. Okay? And what one realizes when you get to this point is that the phi I, you can also see it in my slides, is common always. You have it here, you have it here, and you have it here, right? So it actually cancels. It actually cancels. It appears in all the terms, right? So it cancels out. The way I did it here is I put everything to the left-hand side so that you could see that something multiplied by phi equals to 0, the phi disappears, cancels, doesn't play a role. Okay? It cancels out. That's the message. What you end up with is the equation on the bottom. Okay? It's actually simpler because you only have one summation, not two anymore. You have all the terms with the derivative, so the Young modulus, the area, derivative of shape functions, multiplied by the coefficients, the q's, the unknowns, the ones I put in red in my slides here. These are the unknowns, okay? These are the unknowns, the q's, the coefficients of my displacement. And then the right-hand side with known data once more. External forces and the known stresses on the right-hand side. Right? What is this? What is this? The last equation that says 4i equals to 1, 2, 3, blah, blah, blah. What is it? Sorry?
It's linear.
Linear.
Yes, you can form a system of linear equations.
There you go. System of linear equations. Imagine some people, when I start putting this formula, says, look, I mean, you make me fall asleep. Do it at least once in your life. Do it for a small mesh. 3 nodes. Okay? What do we get out of this? What do we have? We have the integral of EA, and then you start writing the first equation, and the first equation corresponds to I equals to 1, right? And you say, right, so I have the n1 dx, and then I have summation here of how many terms? As many as nodes in my mesh, so 3, because I decided that this is an example with 3. Okay, sorry. So this is dn1, dn1, dx. And this is multiplying q1. Correct? But you keep going with the summation. Integral of EA, dn1, dn2, dx. And this is multiplying q2. Okay? And the last one, oh, I want to keep this in red. So this is Q1, Q2, and the last one is plus the integral EA. I think now everybody starts to see what is going on here. Q3 equals, okay, I've done the whole term on the left. And what do you have on the right? F, integral from 0 to L, F, multiplied by N1 plus 3 times area at the right end multiplied by N1 at L. Yeah? And now I'm not gonna be writing here and you sleeping. I'm gonna copy them and just show you what I need. Right. Okay, let's see if it's working, sort of. Sort of. It's not as easy as I thought it would be. For I equals to 2, let's do a bit of a zoom here. What is changing is the index of the first shape function. I'm not being very successful here, right? That's not what I wanted to do. Go back to here. What I have is dn2 dx, dn1 dx, and everything multiplied by q1, and so on. Okay? Now, what we have is 3 equations with 3 unknowns. I can write the last one, the first term at least. 3 equations, 3 unknowns. The 3 unknowns being the displacement at each one of the points of my mesh, right? So the more points I put, the bigger will be the system. Now, I want to focus at least this time. Today I'm doing quite, step by step everything. It's the first problem. Bear with me. It's not going to be always like that. N3 dx. And I want to talk a bit about the last term here, actually. What is N1 of L? And if it helps, look at the picture. Anyone?
0.
Yeah. The first shape function, remember what they need to satisfy. They satisfy that they are 1 in the associated node, 0 in the rest of the nodes. Okay? So the first shape function, the red one, evaluated at the right end, this is what I'm writing there, N1 of L, is equals to 0. What about N2 of L? Same thing. Same thing. And what about the last one? 1. So it's only one equation that the boundary condition is contributing to the one associated to the point where you have the information. Okay? Right. So let's go back here. Okay. So that's my equation. I just did an example here on the tablet. This is exactly the discussion I just had with you. Shape functions at the left end. There is only one that is non-zero. It's the one associated to the first node, as you can see in the picture, the red one. All the other ones at the left end do not contribute. Okay? And the same for the right end, which is the actual one that we discussed. The only one that is contributing there, the only one that is non-zero is the green. All the other ones are 0. So at the end, this is the kind of system of equations you get. Okay? You have a matrix multiplied by a vector with the unknowns, okay, equals to our right-hand side. Now the matrix, maybe doing the showing the two images will help. Each term of this matrix is of this form. Is E multiplied by A, and then derivative of the first shape function, derivative of the second shape function, which is what you should recognize here. The term, this one is here. This is the term 1, 1 of my matrix, and it contains n1 and 1. The term 1, 2 contains n1 and 2. This is the one. The term 1, 2 contains n1 and n2. And so on. And this is what is in the slides, okay? The first term is derivative n1, derivative n1. So the only thing I've done is a small example so that you can visualize it, not everything so abstract with ends and so on, but it's exactly like that. Yeah? The vector of unknowns, the Q's in red here, this Q's in red. So it's a matrix multiplied by a vector on the left-hand side. Right-hand side, let me go here first. This vector here, the vector containing the information of the external forces, is this vector here. Okay? So is, in the slide, in the handwritten notes, is this part here in gray. Okay? This part here, this part here. Is integral of f multiplied by all the different shape functions. So f and I, and 1 and 2 and 3 and so on. And then this guy. This guy I have 3 times a. So if I look at my handwritten notes, is this guy? 3a in the last position, 0 in the rest of the positions. Correct? 3a here, 0 everywhere. What about this? What about R1? It's actually written there. But is the reaction force unknown, and this is very important, is not known, induced by my impulse displacement. And here is when we are hopefully putting all the pieces together. If I go back, that was the first hour today, I said, look, you do integration by parts and you get the boundary information. And I said, on the right of my bar, I know the stress is equals to 3, so I put it there. And then I said, oops, here there is something I don't know, which is the stress at 0. Right? So I'm going to ignore it for the moment, and I'll come back. This is what I said. This is exactly where I'm going now. Okay? A sigma, what is giving you is a reaction force. Okay? You are imposing a displacement. For example, in a beam, you fix it on the left, you put a traction on the right. There is going to be a force at this point, which is called the reaction force, that makes the beam satisfy the boundary condition. Right? This is exactly this term. But we don't know it. And then one says, so we are in trouble or what? Because we have something on the right-hand side which is not known, really. Right? We don't know the displacement at the first point. We know the displacement at the first point is imposed, but we don't know the reaction. So how do we play with that? Right? And I'll show you this with an example, okay? How to do that. So, I got a feeling that because what I'm going to start, I'm not going to finish it in the 3 minutes I have. I'm going to finish it in here. Right? Have a look at the 2 coming slides, which is showing you the process that I will explain next Monday. Okay? Don't forget, no lecture on Thursday.